These slides discuss Chapter 15, Multiple Regression. This is where we have two or more independent variables, or x variables, that we believe can be used to predict our dependent variable y. So this is where you have multiple x's that you use to predict y. A regression model, the equation that describes how the dependent variable is related to the independent variables. Here, there's more than one of them. The betas or b's, depending on whether we're using our estimation or referring to our population, are known as parameters, and the error term is a random variable. E is the error term. It's the variable or the amount not explained by the regression. So your betas or b's will have the same interpretations, essentially, that they did before. Beta 0 or B0 is your vertical intercept or your y-intercept. It is the value when all of the x's are 0, since now there's more than one x. And then each beta shows the impact of its corresponding x on y. So we use the same basic process that we did before. We have a hypothetical model, we gather data, we use that data to then make estimates of our population parameters. So here's an example. A software firm collected data from a sample of 20 computer programmers. A suggestion was made that the regression analysis could be used to determine if salary was related to the years of experience and the score on the firm's programmer aptitude test. The years of experience, score in the aptitude test, and corresponding annual salary for 20 programmers are shown. So here's our data. Years of experience, test, score, and salary. So we have to ask ourselves, what are our x variables and what is our y? In other words, what independent variables are we using to predict our dependent variable? So let's go back to the question. We want to know, they suggest a regression equation can be used to determine if salary was related to years of experience and the score on the aptitude test. So we want to use years of experience and score on the aptitude test to predict salary. So we believe that salary, y, is related to years of experience, x1, and the score on an aptitude test, x2. So I can go into data analysis, and enter first my dependent variable, my y variable, and then my independent variables, my x variables. And it's really simple. I just do this by highlighting the data. Now note that your two x variables must be next to each other. And as long as you highlight the data labels, it will spit out in this, when it gives you the regression output, it will actually include those. So experience is x1 and test score is x2. So my equation, I used experience and test score to predict salary. So salary is equal to beta 0, my vertical intercept of 3.174, plus 1.4 times experience, plus 0.52 times my test score. So what I've done here, instead of just writing y, x1, and x2, is I've actually substituted in for what y, x1, and x2 were actually, used to run, what they stand for. And that's going to be most beneficial for you when you're interpreting your data. So how do I interpret these coefficients? The beta coefficients represent an estimate of the change in y corresponding to a 1 unit increase in each x when all of the other x's are held constant. So my salary beta, or my salary is my dependent variable. My experience beta was 1.4. But I need to go back and notice that my salary data is in thousands. So that's going to impact my interpretation. So each 1 unit increase in experience will increase salary by 1.4, but that's in thousands. So when I do that interpretation here, I can see that salary is expected to increase by $1,404 for each additional year of experience, holding all other variables constant. In other words, when the variable score on the programmer's aptitude test is held constant. So your beta interpretation, a 1 unit increase in that particular X will increase Y by that beta, holding all other variables constant. Now, instead of typing that out, you could write comma CP, which means ceteris paribus, which just means holding everything else constant. So I can interpret the 0.251 coefficient of my test score in the same way. Salary is expected to increase by 251 for each additional point scored on my aptitude test. Now, it was 0.251 as the coefficient, but again, that's in thousands, so that would be a $251 increase in salary for each additional point scored on the aptitude test. Now I can look at how good my regression is. Before, with simple regression, we just looked at R squared. However, what happens is that as you increase the number of independent variables, or X variables, the R squared value will be artificially increased. So what we do is we calculate something called adjusted R squared. Now, I've given you the formula for adjusted R squared there, but just know that Excel spits out this value for you anyway, so you're just going to look at adjusted R squared. Adding independent variables, even ones that aren't statistically significant, causes the predicted errors to become smaller and thus reduces the standard error. The adjusted multiple coefficient of determination compensates for the number of independent variables in the model. In other words, as you increase the number of x's, R squared gets artificially higher, even if those new x's, those new independent variables, have no impact on y. So we have this adjustment that we can do, which takes out that impact of the additional independent variables. So from now on, when we're doing multiple regression, we're going to look at adjusted R squared to tell us the percentage of variation in y, our dependent variable, explained by our regression. And the higher that percentage, the better job our regression does. The F-test is used to determine whether a significant relationship exists between the dependent variable, the y variable, and the set of all independent variables used. Now, last time in simple regression, we saw that our F-test and our t-test on our only independent variable gave us the same results. That's because there was only one independent variable. Here, however, since we have multiple independent variables, the results of our F and T tests can be different. So what this F test does is say, HO, all of our independent variables together have no impact on our dependent variable. In other words, our regression is useless. These parameters these variables have no impact on our dependent variable. They're not predicting anything. Or HA, at least one of the independent variables has an impact on y, or at least one of the parameter values is not equal to 0. Okay, so we're going to use usually an alpha of 0.05 for a 95% confidence. So if your p-value of your F statistic is less than 0.05, then you would reject HO, and you would be 95% confident that at least one of your independent variables has a statistically significant impact on your dependent variable. So let's look how that would apply here. My significance of F is my p-value of F. That is definitely less than 0.05, so I reject HO. At least one of the independent variables has a statistically significant impact on salary. If I want to be more correct, I can say I am 95% confident that at least one of my independent variables has a statistically significant impact on salary. Now note, I substituted in salary instead of y because y is salary. And it's always best to actually substitute in for your x's and y's where you can in your interpretations so they're more meaningful. T-tests. we can conduct individual t-tests to see how our independent variables individually impact our dependent variable. So they're used to determine the statistical significance of each individual independent variable. So I can do a different t-test for each of the independent variables that I have. In this case, I have 2. They were years with the firm and score in the aptitude test. So HO is beta whatever equals 0. In other words, this variable is useless. This independent variable has no impact on my dependent variable, and HA, it's not useless. Its impact is not equal to 0. It does have a statistically significant impact on Y. So again, follow the same logic. If P is low, reject the HO. So let's look at what we have here. We look at our regression output, and we go down to the regression equation. So here again, our equation was salary is equal to 3.17 plus 1.404 experience plus 0.25 test score. So I can conduct 2 hypothesis tests just by looking at the p-values. So my first hypothesis is beta experience equals 0. I look at that p-value, it's less than 0.05, so I reject HO. I am 95% confident that experience has a statistically significant impact on salary. And then I can conduct a second hypothesis test. Beta test score equals 0. Again, I look at that p-value, that's also less than 0.05. So I can reject HO again. I am 95% confident that test scores have a statistically significant impact on salary.